Hello students, so we will discuss in this lecture another new topic in electromagnetic theory. To start with the topic, here is an example of a multiple choice question that may be asked to you in any exam, that for which of the geometry the electric field is continuous. Now how will you answer this question? There are three options. The fourth one is of course none of these: solid, sphere, hollow sphere, charge sheet. Now to answer this question you have to understand a very basic concept in electromagnetic theory in case of the electromagnetic potentials. And that important topic is boundary conditions and the uniqueness theory. We will come to the uniqueness theorem later on. First we will study the boundary conditions. What are the boundary conditions? Now boundary conditions are very important in electromagnetic theory as well as in quantum mechanics. You have seen that in quantum mechanics the boundary conditions give rise to the eigenvalues or the quantized energy levels. Similarly, the boundaries, they define a lot. They have a lot of information, they have a lot of physics and of course philosophy. Boundary conditions in electrostatics refer to the change in the electric and magnetic field. Now electric field, we are concerned about electric field in this lecture. Electric field or any field, it is a vector quantity and potential is a scalar quantity. Now what is a boundary? The first thing we need to understand this. So if you are given a problem that you have to find the electric field due to a charge density rho when there is no symmetry condition. Now what happens when you have symmetries given in the condition? Then what you do you apply the Gauss law. Gauss law means you draw a symmetric Gaussian surface, and the Gauss law says that the electric field is due to the charges inside the Gaussian surface. The contribution to the electric field comes because of the charges that are inside the Gaussian surface. No contribution is obtained from charges that are outside the Gaussian surface. And you must have solved the problems of Gaussian surface in 12th in BSc first year. The electric field due to a sphere, a hollow sphere and all these things. But when no symmetry condition is given, then how can you find out the electric field? To solve such problems, the first step is to find the potential. We will see how it can be done. The next thing, if you are asked what are the three fundamental quantities in electrostatics, the three fundamental quantities in electrostatics are charge density, rho, electric field E and potential V. Now what happens when you have a boundary, when you have a region or boundary that separates two media? Then that demarcation line is called the boundary. The electric field undergoes a change when you cross a boundary that has a surface charge density. Now the question is, how the electric field changes, or how much, by what amount the electric field changes at the boundary. Now when you are using the symmetry conditions, you are using the Gauss law. The electric field is E dot dA. The flux is due to the charges Q inside the surface, and if you have a sheet of charge with surface charge density sigma, we are considering here a sheet of charge. Sheet means a very thin layer of charge with charge density, of course surface charge density sigma. Sheet of charge has area A. Now the total charge enclosed is sigma A. Now from Griffiths I have taken this diagram to save time. When you have a very thin sheet or a sheet of charge, the Gaussian surface is a pillbox. This one is the Gaussian surface. This one is Gaussian surface. Now, if we consider that the thickness of this Gaussian surface is taking the limit to 0, thickness is very small, means this epsilon is tending to 0. This one is the epsilon. This epsilon is tending to 0. This means this sheet is a very thin sheet. The variation of electric field. Now electric field is a vector quantity. So when you have a vector quantity, what you have to resolve this. If this is the electric field vector, then this is E cos theta and this is E sin theta. Suppose the angle is theta. One is the horizontal component along the sheet and another is the perpendicular component along the sheet. Now the variation of electric field is such, because you know, if you have solved the problem on Gauss law for a thin sheet of charge, the electric field is sigma by 2 epsilon naught. Now the variation of electric field, the perpendicular component of the electric field below the surface and above the surface, it is sigma by 2 epsilon naught, means these two things are adding up with each other. And how it is adding up with each other? If you have, this is plus, if this is positive charge is distributed on this sheet, if you put a test charge, it will move here. If you put a test charge, it will move here. So one will be plus sigma by 2 epsilon naught, another will be minus sigma by 2 epsilon naught. Direction, you have to take the direction. And when you differentiate this, when you find the difference between these perpendicular components, it comes out to be sigma by epsilon naught. So what we conclude, that the electric field changes by an amount sigma, by the amount of charge density when we cross a boundary that has a surface charge density sigma. Now if sigma is 0, means if you have such a configuration that the charge is distributed inside, it is not in the surface, then in that case sigma will be 0 and E perpendicular above the surface will be E perpendicular below the surface, both will be equal. A stands for above, B stands for below, and so electric field is continuous. For example, a solid sphere. So the question that I asked in the previous section, this one, the condition continuity will be found in case of a solid sphere, because there is no charge on the surface. Surface charge density sigma is 0. In this case sigma is not equal to 0. In this case sigma is not equal to 0. So whenever you have a surface charge density, there will be a change in the electric field component. Now what you do to find the electric field component, you use this equation E dot dl. dl means you are going over the boundary and the curl of E is 0. This means, curl means the rotating action, how much the electric field, the vector is turning about. The tangential component of electric field is of course 0. Tangential field means this one is the tangential field. And in the limit of epsilon equal to 0, means Gaussian pillbox or the Gaussian surface is getting 0 thickness. In that case, the parallel components, the surface components parallel to the sheet, they are equal, because this condition is holding. dl is becoming 0. This is L, this total length is L, and along this the parallel components are becoming 0. So the parallel component of electric field is equal to above the parallel component of electric field above and below the surface, they are equal. Now if you are asked, So we can say that the tangential component is always equal to, it is always continuous. This means that parallel component of electric field is same above and below the surface. So we can conclude that tangential component along the tangent of the surface, along the tangent, E is continuous. It does not go any change. The perpendicular component of E, perpendicular component of E is discontinuous, and it is discontinuous by sigma. The amount of charge density on the surface will make it discontinuous. So these are the two equations. One is E, this stands for parallel component, above is equal to E parallel, this stands for parallel component, is equal to B, below means the parallel components above and below the surface are equal, and E perpendicular, this is the sign for perpendicular. Here you have a discontinuity, that the difference of perpendicular components and above and below the surface, they differ by sigma by epsilon naught. These are the two equations. Now how you can combine these two equations into one equation? This is very important, and here we make use of a very well-known concept in vector algebra, that is the normal vector, unit normal vector. That is a very important concept. To combine the two equations into one equation, we combine or we use the concept of unit normal. Now you must understand what is the physical meaning of this unit normal. We use the concept of unit normal, n cap. This n cap or unit normal defines the orientation of the surface, defines the orientation of the vector, maybe it is electric field or magnetic field, with respect to the surface. In case of Gauss law or electric flux, you must have studied this equation E dot dA. This is the area vector and how it is defined by an unit normal. Now suppose your surface is this one and you have a unit normal perpendicular to this, then your flux will be equal to 0. Now if this unit normal, it is aligned like this, making some angle with the surface, or you can better understand it like this: if these are the electric field lines and your surface is like this, then the angle theta is equal to 0, and this unit normal is like this. This is the direction of unit normal. So E dot n is E cos 0, and it is equal to E. But if you have your electric field lines like this and your surface is like this, so this is the direction of electric field and this is the direction of unit normal. This is the direction of unit normal. They are perpendicular, so it is E cos 90 because theta is 90 degree and flux is 0. So this N defines how the surface it is oriented with respect to the electric field lines, or in general the field lines or vector. N shows how the surface is oriented with respect to the field. This is the thing that is described by this unit vector. So to combine these two equations, what we have to do in a single formula, we write E electric field above minus electric field below the surface. Above and below stand for below the surface. It is sigma by epsilon naught and this unit vector n. Now we have combined the two situations, or you can say these two conditions that I described here. Condition 1 and condition 2 in a single equation, in equation number 3. The orientation of the surface or the orientation of the unit vector will tell you how the things are, how the surface is oriented. It is a unit vector perpendicular to the surface and it points from below to the above. You can see the diagram. You will find the diagram in the book by Griffiths or any textbook that is dealing with electrostatics or electromagnetic theory. N points from below the surface to above the surface. This is the direction. Now this is the case of your electric field. Now what about the potential? How can you study the potential? To see the change of potential across the boundary, what do we use? Now potential is a scalar quantity, so it is much easy to deal with. So what we write? We write potential above minus potential below. And how can we relate this to the electric field? By this equation E dot dl, because E is equal to dV upon dl, or it is minus with a minus sign from A to B from this diagram, how the electric field is varying. So you can write the equation for the potential also. Since potential is a scalar, things will be easier to you. Now if this quantity, this length, it tends to 0, if dl tends to 0, then the right hand side will become automatically 0, and what you have, V above minus V below is equal to 0, so V above is equal to V below. So you see that the potential, it is continuous. It appears continuous. But there is one thing. You must have studied vector algebra. I have uploaded some videos on vector algebra. And there the important concept is related to gradient. Now gradient is something, a vector mathematical operation that changes, that extracts a vector out of a scalar, and we know this definition, E is equal to minus del V. This is the gradient. So when you apply the gradient operator on a scalar quantity, you are getting a vector quantity. So electric field, a vector, it is obtained from the gradient of a scalar, and this is very important. So you can write it, this equation, the equation for electric field that we have obtained, you can write electric field in terms of potential. What we have seen, E above minus E below, we expressed it as sigma by epsilon naught unit vector. E above and E below can be written as E above del of E above minus del of, or it is minus, you take care of the minus sign, del V below. You have to take care of the minus sign. So del above minus del V below means we are writing as minus sigma by epsilon naught times n unit vector. What we are doing, we are expressing E as del minus of del V. This can be written in a more convenient way as change in the potential del V above by del N and minus del V below by del N as minus sigma by epsilon naught. This you can write in a more convenient form. So what we have obtained here, now this del V upon del N, this is a very important quantity. Del V upon del N, this is equal to gradient of V, which is electric field, dot N, unit vector, both are vectors. This is electric field, this is nothing but electric field. When you apply gradient on a scalar, you get a vector. This is a dot product of two vectors. So what you conclude here, that the normal derivative of potential can be expressed in this way: the rate of change in the direction perpendicular to the surface. This is how you can use the boundary conditions. These are the important boundary conditions for electric field and electric potential when you are considering a boundary or a surface charge density. So wherever there is a surface that is separating two media, things are changing. You have studied optics, refraction, it is a boundary phenomenon. The speed of light in the two media, the boundary that separates the two media, the speed of light is different and you get a refractive index. Same as the situation here, this surface that has a surface charge density, and if this is the above surface and this is the below surface, the electric field components are different. The parallel component is same. Along this direction you have no change, E parallel, but these components E perpendicular and E perpendicular and E above, they differ by a quantity which is the surface charge density. This is a very important situation. We will, in the next section, we will see the uniqueness theorem and the use of Laplace equations and the energies due to continuous charge distributions. So for the time being, please stay tuned, watch the videos, like, share and subscribe, and if there is any shortcoming or if there is any problem, you can ask me in the comment section. Thank you.